Hello and welcome to Elektor Engineering Insights, the show that puts your engineering challenges to the industry's experts. I'm your host, Stuart Cording. For those involved in the development of embedded systems, you'll have been unable to avoid the clamour around Risc-V. Traditionally, we're used to hearing about ARM, MIPS and even x86. So why do we need another processor architecture? What makes it so interesting to product developers? And how do you go about building it into a product? To answer these questions and more, I'm joined by Martin Croome of GreenWaves Technologies and Simon Davidmann from Imperas Software. So, hi Martin. Perhaps you could just give us a quick introduction to yourself and also GreenWaves.
Yeah, so my name is Martin Croome. I'm Vice President of Marketing for GreenWaves. We are a fabless semiconductor company based in Grenoble in France. And we're making use of Risc-V in the products that we develop.
Super. And Simon from Imperas, a couple of words from you too.
Right. Yes, thanks, Stuart. Yes, so my name's Simon Davidmann. I work for a company, Imperas Software. I'm the CEO and founder, and actually I have a CTO role as well because I'm very much technical. I spent my whole career developing what's EDA tools around simulation and technology like that, and most recently founded Imperas, and we're based in the UK near Oxford.
Super, thanks very much. I'm just going to take a break away from you guys for a second and to introduce today's sponsor, which is Eisler, powerful PCB prototyping made in Germany. If you're looking for beautiful boards, stellar stencils and amazing assembly, visit eisler.net. And if you're new to Eisler, use the discount code LCCBBL to receive a €30 discount and the chance to win a Volterra V1 PCB printer. Just upload your design files by the end of June 2022. So now, while I have plenty of Risc-V questions for my guest, this is a live show and it lives from the questions that you share with us. So if you have any questions and issues that are troubling you, regardless of where you are watching, you can post your questions directly to us. Throughout the show, we'll do our best to get answers or guide you to resources that might help. And between the shows, you can also get in touch with me, Stuart Cording, directly via email or Twitter. So without any further ado, let's go back to Martin and find out some more about the fabulous GreenWaves company and how they're using Risc-V. So welcome back, Martin.
Hi again.
So tell us a little bit more about GreenWaves, why you've started a fabless semiconductor company and what role Risc-V is playing in your product.
Yeah, so GreenWaves is a company that's actually designing chips and then producing them inside fabs. Those are manufacturing houses. That's why we call ourselves a fabless company, because we don't actually do the manufacturing. So we've been in the market for about 7 years. We've got 40 people spread around Grenoble, Bologna, and the sales office in Shanghai. And really, our focus is to deliver processors which are for DSP and AI mixed tasks in devices that are extremely energy constrained. So think of devices that are so small, have very, very small batteries that need to last for a day, like an earbud or something like that, to sensor products which need to last for years on a battery. We have one product in production, GAP 8, which has been out for 2 years, and we have just started to ship our next generation product, GAP 9, to our lead customers. And one point just interesting is that a lot of what we do is based obviously on Risc-V. Risc-V is open source, but we also have a lot of interaction with open source projects, one particularly called Pulp, which comes out of ETH Zurich and University of Bologna.
Super. Now, obviously the GAP, like you said, the GAP 8 product is already out there on the market. What type of applications are they addressing and that need this level of sort of intense processing?
Yeah. Well, GAP 8 was really based on a vision that we developed like 6-7 years ago. And really, we were very focused at the time in the idea that IoT sensors were going to stop being things like temperature and humidity and start having sensors in them which were going to capture much richer data, like cameras capturing images or infrared images or radar or biosignals and so on. And that we were going to need to process that on the sensor at very, very low power, so that we could kind of compress the data down to something simple and send it over a radio network, a low-speed radio network. And that's really what's happened with GAP8. So we've seen GAP8 used mostly in building sensors, doing things like counting number of people in a room, with our products in the market now with GAP8 inside them, which are doing that kind of thing. We've also seen GAP8 used to wake up larger devices. So as something that's always on, looking for maybe a sound or a person or an object or a thing, and then switching something else on.
So it'd be something like the speakers, the smart speakers we've in our homes, looking for like a wake up
maybe a
word
smart door lock,
Okay.
or something of that sort. Again, we're really focused on energy constraints, so we have to be in a situation where energy is important.
Yeah. So with the GAP8 and GAP9, looking at the devices themselves, there's many Risc-V cores in there. I think there's 8 in the GAP8 and around 10 in total in the GAP9. When you started developing this application, obviously there's, as I said in the introduction, there are many other suppliers of IP that you could have used. Why go for Risc-V?
There's a few reasons. One thing's very linked to the fact that we work very closely on open source projects, and our CTO was one of the co-founders of the Pulp project at ETH in Nunabo. And in fact, at the time, they weren't using Risc-V. They were using another core. They were using OpenRisc, which was a precursor to Risc-V, and actually moved across to Risc-V. What Risc-V gives us in the context of working on open source research projects is a kind of IPR license-free environment that we can work with those universities. So we don't get into the kind of discussions that sometimes are quite complex with universities about who owns the IP at the end of the project. That's our kind of research wing. Yeah. Then we take that, obviously, that IP, and semiconductors are a complicated area where bits can be open source, but other bits cannot be open source. So we take that and then we build a chip out of it with IP that we develop, IP that we buy, and obviously all of the secret sauce we put into integrating all of this. And then that kind of comes out. The second thing that Risc-V gives us is the ability to innovate around the instruction set. And this is quite unique. And at the time when we started GreenWaves, was probably very difficult to do with ARM. At the time, it required an architectural license, which would have been extremely expensive. This is less true these days, but it would have been a problem at the time because we didn't have a lot of money when we started up. We had a vision which 7 years ago, putting AI into a battery-powered device was considered to be a somewhat silly idea. Now it isn't. So that ability to actually innovate both in terms of the instruction sets that the cores implement and also in the memory architecture and the architecture of the cores and how they're implanted inside the chip are two things which are very important to us. And as an example, just in the instruction sets, the ability to innovate in that area can give us, just on a single core, 3 to 4 times more energy efficiency than if we didn't have that ability. So it's quite significant.
So the Risc, I think it's important also just to highlight that Risc-V is an instruction set architecture. It's an ISA, and it's basically a document, I guess we could describe it as.
It's a piece of paper. Yep.
Exactly, yeah, that describes how this processor architecture is constructed and also has descriptions of how a limited set of instructions function. And a company like yours can go in there and just take some of it or all of it. And there's also, as you said, that gap for custom instructions as well. But obviously, and as an ISA, it's also open source, and open source is then immediately linked to free. But obviously, it isn't free just to build a chip. So, so what are the financial costs involved in bringing one of these things to market? Is there an open source VHDL or Verilog core that you can just take, or do you have to actually develop that core yourself? Is that the best approach when you're developing?
There are a ton of cores around, both open source and also cores where you can license designs of Risc-V. There are cores that you can run on FPGA that you can download, and you can, get an FPGA and run them straight away. So yeah, you can do a lot of playing around with Risc-V as a hobbyist quite easily. Obviously, when you start to make a commercial SoC, the costs involved get quite a bit higher quite quickly. Basically, the costs are driven obviously by the process that you're producing your chip in, and then mask and production costs are very, very high. But there's a couple of things which Risc-V kind of adds in that area. And you're right in saying, Risc-V is just a load of pieces of paper, but it's also an ecosystem that's around those pieces of paper that are development tools. They're getting, GCC to run with and compile code to Risc-V and support all of these different extensions and so on and so forth. Companies like Imperas who are within that ecosystem of companies that are producing tools for Risc-V, and that's super important, because without the tools, if we were to come with a chip with some specialized instruction set architecture and go to our customers and say, hey, use this, they're going to go, well, no, we don't want to learn any new tools. Does it support GCC? Is there a GCC version for it? No, we don't want to program in assembly language, and so on. So the tools are super important around it, and that's part of having this very rich, and very large companies supporting Risc-V. And this slide is actually talking to some of those points in the sense of, some of the things that actually are causing Risc-V to be there. One thing which is quite important is that a lot of the Risc-V that's actually out there, you don't actually see. It's all embedded microcontrollers inside things. So if you're building, for example, a power management device and you want a little core, well, you can just take a Risc-V core, download it from GitHub, and start using it. And in a lot of cases, these cores have been looked at by lots of eyes, and lots of eyes means less bugs. And probably better security as well. So, those things are really, really nice from a designer perspective. And that's where Risc-V has really, been very, very successful. Most people now, I say, most chip designers, if they need a core, they're not going to expose it to a customer. They'll use a Risc-V core or something very like it. And that kickstarted the development tools. But we're using Risc-V really from a perspective of innovation, and not really from a perspective of, hey, it's free, because making a chip is an expensive thing to do.
Yeah. So Risc-V as a processor, obviously that's available there, but then there's also other sort of standard bus interface, like I think it's the Amber bus is commonly used for data and address communication with memories, and then you've also got the peripherals. So how do you make a decision as to how to interface everything on the chip, and how much of your time is spent on Risc-V development compared to developing all the other features and peripherals that you want inside your GAP9 processor?
I think that's the second point is the key to this, is that we really, Risc-V is definitely important to us, and the cores are definitely important to us, and the core design is definitely important to us. But there's so many more things to GAP9. There's all of the interface stuff. There's a very sophisticated architecture, in a sense that GAP9 is a combination of a compute cluster with, as you said, 9 cores inside it, plus a microcontroller core with a very advanced peripheral management unit with very low latency DSP capability, all kind of inside this one chip. And those things are all either IPs that we've developed completely in-house, or IPs that we've developed as part of our open source partnership with Pulp, or they're IPs that we're buying. And in the end of it, the core itself is actually quite a small portion of that. But as I said, coming back to it, it does allow us to get these kind of benefits. This is an example of just adding a few instructions to an ISA, and what that can do in terms of speeding up a particular operation. Now, adding instructions is not something that you do kind of all the time, because obviously if you keep adding instructions, you end up with a core which is huge and uses a load of power. And since we're very interested in having low power, that's not a good idea. But some things, where there's a really general case, and in this case, there's three things going on here. One is post increment stores and loads. The other thing is vectorized dot products, 8-way vectorized dot products, and hardware loops. And if you add those three things, you're going from essentially classic Risc-V 32 IMC instructions to these extra instructions. You essentially get 9 times less instructions. So in fact, what happens is that this loop executes 4 times less, and overall there's 9 times less instructions. And that's the kind of, and the benefit to us is, these extensions were specified over 6 years ago as part of the Pulp project.
Yeah.
And in Gap 8 and Gap 9, they're already there. And if we need something new, we just specify it and it's already there. Okay, yes, we've got to do the verification. We've got to do all of the things which are very important from a chip perspective. But it gives us an amazing ability to innovate and to innovate and to bring something which is really good for our customers to market.
So how does that innovation present itself to the code developers, the embedded system developers that are using it? When they're using GCC, are they able just to continue to write C code and those extended instructions are all absorbed and used as required? Or is there still a certain amount of inline assembler that needs to be done in order to make use of these extra capabilities? Great question.
In most cases, the optimizer, we've enhanced the optimizer in GCC to cover these instructions, these extra instructions, and there are other standards type things happening around these kind of instructions extensions, which are helping that to get into other tools as well. So in most cases, things, for example, like a hardware loop, where there's a loop setup instruction, which you can see there, where you don't need to do a test in each cycle of the loop, that's going to be detected by a compiler. There are some things that probably don't get detected by a compiler. And in fact, this dot product instruction that you can see there, which is actually a 4-way 8-bit dot product, vectorized dot product, so MAC and accumulate, so it's doing 4 max at the time. That's something that's quite difficult for a compiler optimizer to spot. So there we have built-ins in the compiler that you can select that instruction. But in general case, the optimization just happens.
Now, of course, if we look at the microcontroller industry and the embedded processor industry, somewhere where I've worked for the last 20 years, most people are quite content to put a single core on a chip and deal with all the complexities of that. But you've gone straight into developing a multi-core processor. What are the challenges of putting more than one core on a chip, from the perspectives of designing the chip through to interfacing it, and then, of course, to getting the most out of it when embedded developers want to program on it?
Yeah. Well, first perhaps give a little bit of background why we did it, because that will actually lead to the other answers to the other questions. Essentially, one of the base things that we're doing is exploiting parallelism inside algorithms. And that's because the algorithms that we're doing are really highly parallelizable. We're really doing a mix of DSP tasks and neural network type tasks. Well, neural networks are very, very what you call embarrassingly parallel. In the sense that you can split up the problem and just run it on separate cores. Now, when you run something on separate cores, you've got 8 cores instead of 1 core, you're hopefully expecting the thing to go faster, right? So that's known as speed up. So ideally, you would like it to go 8 times faster if you've got 8 cores. Well, of course, the real world, there's another problem, which is data, which is getting data to those cores and feeding them data so that they can work. And you need to feed them data in something that's very high speed so that those cores can load and store to that high speed thing. So the main challenge with multiprocess is that high speed thing, getting the data to them. The second challenge with multiple cores is that every now and then you need to synchronize. You need to come back to a point where you're running something on 1 core and synchronize, and then fork again, go out to the 8 cores. And basically you're constrained by this single core task. It's known as Amdahl's law, and it's constraining in terms of. So that's the second big constraint that you get in a parallel system. So we have some tools that we actually deliver with the chip, particularly a foundational tool that we call an auto tiler, which is something which actually chops up all of the data that's presented to kernels that you're running on this compute cluster, chops it all up and moves it in and out behind the processing that's going on. And it's a tool which actually generates C code. So it generates the code necessary to do all of this movement that you can read, that you can debug, that you can see afterwards. And also, of course, we have huge kernel libraries covering tons and tons and tons of different things. Processor companies, we're a hardware company, but we have more people doing software than we have doing hardware, like most hardware companies.
I was going to say, it sounds like a familiar story. So I'm just going to take a break there for a minute and see what questions have been coming in while we've been talking. So actually, there's quite a few comments coming in at the moment. So here's an interesting one. We've got E2JW from Denver, Colorado, and they're asking, how do you distinguish this DSP from existing ADI and TI DSPs that are already very power efficient and computationally powerful? So
I've got that extra slide at the end, just past the last one, which would be a great one to bring in there.
Okay.
So how is what we're doing different to a classic DSP? Well, it is very different. A classic DSP is generally what's known as a very long instruction word computer, which means that it takes in a big instruction word with loads of instructions in it, which the compiler has scheduled. And we don't do that at all. We have essentially what looks like a kind of micro high power computing compute cluster with a shared memory area. So these are free running cores. So here you've got 8 synchronized. So they're synchronization primitives, but free running, their own program counter cores. And basically that allows us to parallelize things in a much finer grained way. With a VLIW kind of architecture, you're really relying on the compiler to parallelize things, whereas we can actually just fork something out onto all of these cores. To give you a kind of an example of how that benefits, versus an LC3 is a Bluetooth Low Energy codec. If you look at that running on a Hi-Fi 5 versus a GAP9 cluster, GAP9 cluster will be using about 2 times less cycles and 3 times less power per operation, so giving you a total of about 6 times less energy use. And then we combine that with some specialized computing blocks, NE16, the smart filtering unit, which I think would take too much time to go into.
Super. Well, thanks very much for that. I also have experience with the TI DSPs and low power, so it's interesting to see the different approach there, and I hope that E2JW from Denver, Colorado was happy with that answer. Hello also to Prat H from the USA and UFlip from Germany. Thank you. And Annie also for joining us today. I have another question from Matthias, and his question is, why have you decided to use the Pulp core and not one from Sci-Fi, for example?
I think I think I kind of highlighted this in the sense that we have this very, very close working relationship between ourselves and the Pulp team. And kind of, Pulp team and the open source work that we do with the Pulp team is really, really almost like an extension of, our research and development in a sense. And we feel that open source is super important in that, that kind of interaction of open source between a real open source university producing open source designs and ourselves is a really important thing. And, doing common test chips, doing stuff like that. And that's not something that we could do with a commercial company. So it's a different relationship. It's not, we don't need another arm. We need this kind of different working relationship. It works for us, because we have a very skilled set of chip designers who've got tens and 20s and 30s of years in the industry. So would it work for everyone? I'm not sure.
Okay, well, we'll leave that with Matthias. I believe he's in our Elektor lab, probably downloading the code for that currently to download to his FPGA, because he was talking about that last week in their live stream, the Elektor Lab Talk show. Super. Well, thanks very much, Martin, for all of that insight and input on using Risc-V in an application. What we're going to do now is move over to Simon from Imperas and have a look at how those processor cores are actually then designed into a chip and tested. So Simon, welcome back. Thank you very much.
Right, yeah, thanks. And to get my slides up,
There we go.
Click a button. Great. Okay, yeah, thanks very much. And I'm from a company called Imperas, and we funded this some 12 years ago. And as I said before, my background's from the sort of EDA technology, where we've been building simulators. I've worked in the cadences and the synopses with technology, with leading simulation technologies and verification technology there. And one of the things we found in the industry, our customers all being sort of chip designers, is that nobody would design a chip without simulation. It's just a standard part of the tool chain. Yeah, there's lots of other tools, but no one would do it. And what we found was that, sort of 15 years ago, everyone's building electronic products, and all of those products were going to be defined by software, is what we believed. And what we realized is that people were not doing simulation. They were just running the software on prototypes and everything, which is a real challenge. And like nobody designs a chip without simulation, we believe that nobody should develop sort of embedded software and firmware without simulation. Got to use technology to do it. It's far too complex, especially when you have more than one core, with several cores or interacting in there in different bits of the design and everything. And so we build simulation technologies and tools and debuggers and models so that we can build a simulation model of an electronic product which behaves exactly like the hardware. So the software can be developed and got up and running without the prototyping, without the silicon. And we also help people getting the designs correct. And one of the key benefits of that is that you can start with the simulation way before you've even got started almost with the RTL. And, we had one of our customers, it was a 1.2 billion gate inference engine, actually.
Wow.
They'd actually got their simulation framework and everything up and running on the simulation 18 months before they taped out the chip. So they had a long time to flush it all out. And it was fantastic. So it can help people really shrink the development time. So Imperas background, our focus is tools to help people do electronic product design around simulating their processors. Okay.
Yeah.
And so to look at the types of tools we have, and there are a variety of different things. The key central bit in the blue bit is what we sort of call a virtual prototype or virtual platform. And that has models of CPUs, models of behavioral components, peripherals and things in a sort of an electronic simulation model of a hardware platform. And that is designed in such a way that it can run the software without any changes. So we can take the same binary you might run on an existing design, and it'll just run on one of our virtual platforms. So it allows you to really get the software correct very early on. And that runs on a simulator. We have a very sophisticated sort of simulation technology. You get that up and running. You can have some sort of test bench technology. You can get your full operating systems and everything to run. And then we have this technology we have debug technology, so you can control the software running. But we also have these other analysis and verification tools, which allow you to monitor what's going on as the software is running in a non-intrusive way and analyze what's happening. So, you can run it through the debugger, see what's happening, sure, but we can actually look not just at the instructions or the C, but we can watch how the operating system is running. So we can profile running software, we can look at the code, we can see what's going on at a detailed level across the whole platform, where we can look into multiple processors and multiple processes running in the software. And we can do very good controllability and visibility of what's going on in the software. And that's very important, because modern electronic products are really complicated with lots of processors and components. And so you really need good insights in tools that you can run in your continuous integration environments and run very efficiently in that. And one of the big challenges, if we move now to sort of the Risc-V part of this, so is the complexity of the modeling that you need. And we heard Martin talk about Risc-V and the freedoms it gives you. One of the key things that they did very well with Risc-V is say, okay, there's a basic set of instructions, on 40 instructions, which is a base, and then on top of that we can layer extensions, instruction extensions. So they could be maybe for mathematics, where you've got hardware multiply and divide in there, so you don't have to do it in software. They can be for the floating point that you can add in there. Vector stuff, as Martin was talking, hardware loops in the pulp. So you have all of these, the ability as part of the design of the ISA to extend it into, and give you the freedom to have basically hardware running software to target different application areas that your electronic product may have. And one of the key challenges in sort of modeling this is Risc-V. Yeah, there's basically 40-something basic instructions, but with the standards that are out there being what they call ratified or being ratified, you get up to almost 1,000 instructions, because there's 300 vector instructions, 300 DSP instructions. So there can be lots of ones, and you can choose which ones. And from our point of view, we've got customers who need a reference model of these. And actually these standards evolve, and you can see there on the slide, the different, down the page, different extensions, but actually across the page, the different version numbers. And one of the key things that you need from a reference is to be able to dial exactly the configuration that you're putting into your design, or that you've got access to. And so one of the things that a lot of people are using Imperas for as a reference is because we have that configurability in there. And Risc-V really for Imperas is sort of the last 5 years. Before that, and still today, half our business is around ARM and the other processors. We were used by a lot of ARM customers, a lot of MIPS customers, PowerPC, all of these sort of embedded electronic products. And Risc-V is a relatively new one for us in the last 5 years, and we've become basically the reference model for that. And to use that model, yes, we can use it in the virtual platform, so you can boot your Linuxes and develop software on them and everything. But also the challenge is that everybody can design their own processors, and so they need some form of verification environment in there.
Yeah.
And on the right here you can see that, okay, sorry, in the middle people have a design and they'll have some memory and things around it in the core. And then on the right, they're going to have some form of test bench, so they can stimulate it and control it and clock it and maybe monitor what's going on and put random instructions into it to test it. And they need some form of verification to know, well, does their design, the pipelines that they're implementing and everything, does that actually match the Risc-V specification? Does it function correctly? And one of the things we've done is we've used our many years of experience in the verification world and the hardware EDA world to build a technology we call Imperas DB, which is a verification environment that can just sit behind your test bench and monitor, sort of like an assertion, everything that's going on in your design at an architectural level. So you can run tons of software through it, and at every event, every instruction, every exception, every debug event or interrupt, we're comparing the full state of the reference model against your design. So it makes it very easy to see if your design is actually complying with what you're expecting to do, the spec and the standard. And the great thing about our model is because it's very configurable, it can be exactly what you've chosen to implement, the subset or your own. It's very easy to extend it with custom instructions, because one of the beauties of Risc-V is you can add your own instructions to it. And of course, our model allows you to do that. And it's hooked up by, there's a blue line called RVVI, Risc-V Verification Interface, which is a standard that's starting to be adopted to be an interface between the reference components and the cores, which means you can get reuse and things like that, which is very important. So, Imperas were involved with 3 different things, really. The modeling of the components, the tools which allow you to develop software on it, and then the verification environment for the Risc-V processors. Okay.
So, as you were saying there earlier, the Risc-V ISA is obviously based on lots of individual parts. We've got, for example, the integer instructions, we've got some of the floating point instructions, and there's different versions of those, the vectoring extensions, there's lots of different versions of those. As a user of a Risc-V based processor or microcontroller, is there some sort of set of registers where I can read out and find out what version is actually implemented on that device? How do we sort of communicate to the compiler which instructions are actually available?
Yeah, so that's a really good question, Stuart, and it's been quite a complex path to have been trodden by the Risc-V world, the ecosystem in there, and because it has evolved, and there's several different ones moving forward. But what Risc-V International, the body out of Switzerland that looks after it, which is a global organization, a non-profit that we're all members of, what they've done is they've set up, a very sort of controlled process of getting them standardized. And you can see on the right of each one of those, there's 1.0, and that's what they call the sort of ratified specification. I think actually only the DSP is not yet ratified on this, so it's still evolving. And what happens is that all the different groups will work and evolve it, and they'll sort of publish an interim version, and the tool chains will work on it, the models will work on it, people will be trying to implement it in silicon, in RTL. People don't tend to go to silicon, but until it's ratified, and that is where everybody's sort of happy that that subset is sort of good for purpose, it's firm, it's flushed out with most ambiguities gone, and there's a sort of cooling off period, and then the board and everybody accepts it and it becomes ratified. And that's when the tool chains and the tools like the compilers tend to be upstreamed into the main line of GCC and LLVM. And so typically most people implement from the 1.0 versions, unless they're doing something special themselves, where they'll either work on the development one, and then that's up to them how they do it. And they tend to be involved actively in the working groups on that, or they build their own solution, like the Pulp guys did a very good set of instructions, which some of those are just nowhere near Risc-V yet in the standards, like the hardware loop stuff, because it does a very good job, and at some point there might be a standard version of that. But yeah, it is one of the challenges is what version. But most people go with they wait until it is standardized, because what you want is the support, as Martin said, from the ecosystem, where you need all the tool chains in there. You don't, and what the tool chains guys have done is said they really only want to upstream things which are stable and ratified. And what's happening is that there's a new initiative in Risc-V International, it's been going 3 years actually, to work out what they call profiles and platforms, because you've sort of got a smorgasbord of 30 different extensions you could have, but actually, what are you going to have? And they're trying to put them in packages to say, okay, this is one for a pretty comprehensive embedded controller. This is the components it would have. It'd probably have these 5 things, whereas an applications processor wanting to run Linux, it's going to require these. And so the Risc-V International is working with its groups underneath it, but also with the tool chains, part of the ecosystem, to try and bring that together so that there will be sort of standard clusterings of these things. Okay, this is this application, this is that application. But it is stabilizing. 3 years ago, it was like walking across a marsh. It was quite difficult. But we do have a lot of customers that do have dotted versions, because they've gone, okay, we're going to RTL with this, and they've gone to vectors in 0.71, and they end up having to help a lot with the tool chains, and where some have gone bit per minute 0.92 and some 1.0. So yes, it is a challenge, and one of the things is been very good from an Imperas point of view, because our modeling technology was built originally to deal with the arms and the MIPS, which kept evolving as well. We had this technology. So with Risc-V, we've got all the dials and switches to do that. So our model is very good at being selectable to exactly the design that the person has. So it's good for the software that they're putting on it, and it's good for the verification point of view.
So I think one of the other key elements of Risc-V that obviously Martin has touched on is this ability to develop custom instructions, which isn't really something that's possible for other processor architectures that you buy, or not in the same level of flexibility, let's say. So if I want to develop a new instruction, something like this dot vector product that Martin was mentioning for the gap processors, how do I start? Do I sit down and start developing some VHDL code and try to develop from there, or is there a higher level modeling process that I can use just to try out the concept of an instruction?
So I think if you wanted a dot product, you'd probably go with the Pulp one and go with Martin's. You wouldn't need to, to reinvent that. But yeah, it is. I mean, I think that's one of the key innovations really of the Risc-V technology. And it's interesting, Martin talked about open cores. I'd sort of forgotten that when we started Imperas, we wanted a technology we could use as a demonstrator where we could get a sort of the RTL, get a tool, get it to compile. And we actually was, for the first several years, we used a lot of the open core stuff, but obviously we moved to Risc-V. But so, yeah, I mean, I think that with Risc-V and custom extensions, the thing that Risc-V does, which nobody else does, is it gives you complete freedom to extend it. It. As part of the fundamental design, it says, this area is for extension. This is, you can add things here, 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 and here, and it won't get in the way of the rest of the solution. And that was a brilliant concept for this extendability. And I think that that's the key thing it gives, is this freedom to innovate. Now, it doesn't say the other companies don't have it. MIPS had a way of extending it. And actually, we worked with ARM. They've got some ways of extending their instructions in a more controlled way than Risc-V. Risc-V, in some way, could be a complete can of worms because you can do anything you like. Which is dangerous, but that's okay, because it means you don't have to invent. If you're just using it for yourself, then that's a perfectly good answer. If you're trying to be part of the sort of standard so you can make use of all the tools, you are constrained a little bit. But what it does is it gives you freedom to do two things. One is add your own sort of state and instructions. You can just add to it, and there's a very clean way from an ISO point of view to do that. But also from an architecture, you can put the cores together with this network on a chip or this type of bus, or they could lockstep each other, or they could be in all these different processing elements. And, so we have people with hundreds of cores on their design, all different configurations. So it gives you complete freedom. And I think that it could be a real challenge to how to do that. And one of the things that we've done with Imperas, just plug Imperas a little bit, is that, we designed our simulation technology. So you have the basic, what we call our envelope model, which is the Risc-V standard and all of 200, 300 configuration options. Then we have the ability to add as sort of an extension library, your own versions of it. And because all our models are sort of open source, you can see exactly how we've done things. And then you can add things on top of it without touching the envelope model. You can add your own instructions, your own state, your other things there. So we've got a technology which allows you to extend it all in source yourself. So it's in using all the APIs we normally use. And the thing we've done, which actually I think is very good, is that if you add these extensions, then all our tools work with it. So that, our debugger works with it, the disassembler all works with it, the breakpoints, the tracing, the coverage, the profiling, everything just works with your own instructions. And because for us, it doesn't matter whether it's internal or external. And so I think that the great thing about Risc-V is it gives you this freedom, but you have to be really careful, because it gives maybe inexperienced engineers too much freedom. And I mean, one of my colleagues who spent years works in Imperas and worked in ARM, MIPS, and Imagination, actually, he said the challenge that people don't realize is that if you add another feature, you're doubling the amount of verification you've got to do. So it's easy to say, just add this little verification feature here, but actually, the complexity, so that it gives the engineers freedom, but I think the management needs to be a bit more structured, especially with the verification, because you need better metrics and what you're trying to cover and how you do the functional coverage. But there's in the hardware design world, there's been 20, 30 years of experience from the main guys, how you do, verification for blocks and for, and actually you mentioned VHDL. I'm the last person to ask about that, because I was one of the developers of Verilog and System Verilog, so you don't talk to me about HDL. But yeah, an HDL, yes.
Yeah.
And I would just say, though, that, I look at it from a modeling point of view in Risc-V, but there are several companies that we deal with, like, there's the main IP providers out there for Risc-V. They all have solutions for extending, whether it's from their own sort of scripting language with their own tools. They have ways to add to it and extend that. And from a verification, from a reference point of view, we have models of these different vendors' cores, because we've got like something like 80 different models of Risc-V now. And they have ways of extending them. So our technology allows it to be extended based on their inputs. So we work with these people, and so that, yes, you can just randomly write RTL and write models, but actually there are, if you choose an IP vendor, they often have ways of, in a controlled way, to extend it, to make to handhold you through the process, which so But just to sum, Risc-V, it's about freedom to innovate.
Super. And just one last question around this area of tools and modeling and verification. Obviously, Risc-V open source, people are automatically thinking free, but you're running a very successful business. How far can I get on no money when I want to use tools to work with Risc-V, verify designs, develop custom instructions before I actually need to put some money on the table?
Yeah, so you're right. I run a company which is a commercial company that we make money by building products to help our customers get their silicon designed. Right, that's our focus, is to help customers get to silicon. And but we realize that that we live in a world where open source is a fantastic thing. We are a big supporter of open source. We use a lot of it ourselves internally, but we believe it's a very good idea. And Risc-V isn't actually open source; it's an open standard, like C is an open standard, right? And so that's what Risc-V International does. But there's an awful lot of great open source technologies out there, and so how far can you get now? If you want a compiler to take C and turn it in, absolutely, GCC, LLVM. I doubt there's going to be many commercial technologies. If you want a debugger as well, there are like that. Where if you want a synthesis tool to take from an HDL and turn it into place and route, I think there are big challenges there. And so I think, or a simulator. We have a commercial simulator. We actually give away two levels of free simulation as well to try and help the industry from our OVP World site. And we have a GitHub where you can download a reference, which actually a lot of people are using their Risc-V OVP sim in there. But I think, from a open source point of view, there are some very good tools out there. Risc-V, the base stuff isn't too hard. A grad student can build a pretty good simulator. Mm-hmm. But will it have all the versions? Will it be accurate? Will it be used by many people as their sign-off simulator to silicon? And I think that people do get confused with this sort of freedom, open source. And I think the thing, the pragmatic view for me is that Risc-V gives you the freedom to innovate and build the next generation of fantastic electronic products. That's very different from, can I do it with free tools? Now, the customers we tend to deal with are the people that are looking to change the world, change the marketing, building the next technology that does this, that, or the next thing to capture a change in the world, whether it's earbuds here or whether it's a data engine, huge data center. And so I think that, yes, you can get done. There's open source technologies out there. It's good technology, all sorts of things. But if you need to get something done quickly with high quality, where you've got commercially, you need somebody on the end of the phone when you don't get something right or something breaks or something, you need support, you need some help, then what we're finding is that the sort of serious chip guys are using serious solutions, and you have to pay. You sort of get what you pay for. It's not quite fair, because but the customers we have tend to be people that are doing very complicated things. They're very concerned about security or quality, and they want to use sort of best-in-class technologies and people that have had a lot of experience in that space.
I guess the nice thing is, if you're in the position that Martin was, where you're actually trying to start a semiconductor vendor and you want to prove to maybe investors that your idea and your concept can actually work, then obviously for no money or little money, you can actually make that kickoff and starting process.
Absolutely, you can build sort of early demonstrators and all that sort of stuff. I mean, where would we be without open source? I mean, the whole web is, everything
based upon it. Yeah,
absolutely. It's fantastic.
Smashing. I'm just going to go back to our questions and see who else is popping questions in for us. A quick hello to Chris Rao, and also to Dieter Brunzel, who's based in Germany. Now, Chris Rao has a question. He says, are there any plans for implementing the Risc-V pulp core in sub-threshold voltage silicon circuitry? Now, I don't know if you know what the pulp guys are up to. Maybe Martin, has there been any discussion of that sort of using that sort of silicon process to develop a core?
Gap 9 is actually operating pretty much near threshold, so it's 0.65 volt cores, the lowest core voltage. I'm not really aware of and if I was doing something or we were doing something, couldn't really discuss what we were doing.
No.
So
Yeah.
That's
Okay.
gap 9 is at 0.65 at the moment.
Yeah. And then another maybe a question for you, Martin. You mentioned it a little bit earlier. Risc-V as well. This collection of documentation that describes how it works and so on and so forth. But who's actually in charge of looking after this great project? And how would I or any of our viewers get involved?
Oh, the Risc-V organization. Yeah. So there's an organization that's international organization, head office is in Geneva, which shows also the fact that it's trying to be neutral as an organization. And there's a load of standards committees that are within that organization. There are student memberships to it, and then there are company memberships to it, and there are work groups that you can propose yourself onto inside that organization.
Okay. And perhaps to Simon, if I was interested in actually trying out some Risc-V core and learning a bit more about the tooling that goes around it, where's the best starting point for me?
Well, actually, I think a search on YouTube is probably a good thing, because there's a lot of YouTube, and Risc-V International, as Martin said, out of Geneva, they hold these summits and forums, and they record most of those presentations, and they're all on YouTube. And a lot of it's going to be a bit academic and evolving the extensions and things, because that's what they're very excited about. I mean, from a you see, at the conferences, there's people demonstrating the tools. There is a whole ecosystem of IP providers and tool vendors. And if you look at Risc-V International, go and have a look at the list of members. They go to link, and I would prod some of the vendors and say, look, we're interested in this. If you want something open source, just to plug what we do, on one of the slides I had something, I didn't talk about it, called OVP, Open Virtual Platforms, ovpworld.org. In there, it's on the bottom of my slide too, I think. Yeah, down there.
There we go.
This is one of the things, when we started Imperas, we realized that we wanted to build the simulation technology, but we didn't want to really build all these models. We wanted to create an API which we could be as a sort of an open standard, and then we built a lot of models and made them open source under Apache. And people can go to OVP World, they can register and get a 90-day license to pretty much all of our simulation technology and models using all these open source models. So we got models of ARM booting, SMP Linux, some Risc-V stuff, MIP stuff, all of these different, it's like 300 behavioral components and processes there, about 50 different platforms with different RTOSes and that can run and open source, and there's debug so you can do that. So you can get there, and we set that up to try and educate people about developing software on virtual platforms, virtual prototypes, OVP World. And people can download a 90-day evaluation. For hobbyists, we can let them extend it. We provide it to hundreds of universities that use it for teaching. And for commercial users, they can use it as an evaluation vehicle and hopefully come and see something like they like this. So we help educate people, they can explore. But obviously, that's only the technologies that Imperas provide. If they want to look at some of the open source stuff, go to the GitHubs by Risc-V and drill down from that, because there's a tremendous amount of technology. I mean, and that is one of the challenges with open source. There's 100,000 open source repositories, and there's probably only about a couple of hundred that really are useful. And
right.
Is finding those. But Risc-V International, there's a lot of pretty good stuff out there. But
Yeah.
And Risc-V International also, I think, has a sort of an education bit to it. We don't tend to.
Yeah, they do. They have an educational university program that they
Right.
do, and there's a lot of materials around that as well. I would also encourage you to go to the Risc-V international site website, and they've got lots of pointers on that to different things.
Yeah, and I think, and Martin said is, I think as an associate member, as an individual, you can just sign up. There's no cost, I don't think. Obviously, commercial companies have to, or institutions have to pay different amounts going all the way up.
Yeah.
But and if you join that, you can basically just visit any of the working groups, and any day there's about 4 or 5 going on. And some of them are very technical. Some of them are going to be around education, and some are around platforms. Some are around. They tend to be around the ISA though. They're not around where can I get an open source core. There are other organizations like Open Hardware or Chips Alliance that you can focus on if you want to download sort of quality open source things. You need it sort of maintained rather than just a random website. So I think that there's a lot of people will help people
I think one thing to remember is that the Risc-V at its origin was an educational tool. I mean, it was developed by Professor David Patterson, who was the originator of Risc, as a teaching tool to show people, if I change this instruction layout, what happens to my core design?
Yeah.
So it is a teaching tool. Now it's gone way beyond that, but definitely its roots are in teaching.
And I think if any of our viewers want to find out any more about Risc-V, the website from Elektor, elektormagazine.com, has also lots of articles where Risc-V is mentioned. And my colleague Matthias Clausen showed an FPGA board running a Risc-V core recently, and I've written a few articles which explain what Risc-V is. And we also covered the Risc-V based ESP32 in a recent blog post on the website. So we also have that there. We're quickly coming to the end. I'm just going to see what other questions we might have here and comments from our audience. There's Gerrit Yace as well. He's only just got home, unfortunately, so you've missed quite a lot to answer your question. But of course, you can watch, exactly. You'll be able to come back onto YouTube or go onto LinkedIn or even Twitter and see a replay of the video and find out all about what Imperas and GreenWaves have been doing in the field of Risc-V technology. And also on Twitter, I think we've covered all the key points. So that only remains for me to say thank you very much to my guests today, to Simon from Imperas and Martin from GreenWaves Technology. Thanks so much for your time today and providing all those engineering insights around Risc-V usage, deployment, modeling, verification, and your contribution to the Risc-V community. Thanks, guys.
Great. Thank you very much, Stuart and Elektor.
Yeah, thank you, Stuart.
Goodness.
So that's all we have time for today, I'm afraid. That's gone wrong. So my takeaway is that Risc-V is really offering engineers a processor architecture that allows them to innovate without just relying on the next Moore's Law breakthrough. Many thanks to my guest today, Martin Croome from GreenWaves Technologies and Simon Davidmann from Imperas Software. I've really enjoyed the insights you've provided us with today. Coming up next time, in preparation for the PCIM exhibition in Nuremberg, I'll be exploring wide bandgap devices such as GaN from InnoScience and learning how engineers migrate from silicon MOSFETs to these devices. We'll also be asking our guests when it makes sense to transition and which applications currently benefit the most from wide bandgap. If you've enjoyed the show and want to see what else we've planned, you can also drop by the Elektor Engineering Insights page at elektormagazine.com/Elektor Engineering Insights. And don't forget to take a look in on my colleagues Jens and Matthias in their next show, Lab Talk, streaming live on the 28th of April. So that wraps it up for today. Please like, subscribe and share wherever you are watching. And don't forget, if you'd like to join me as a guest, write to me via email, drop me a tweet, or reach out to me, Stuart Cording, on LinkedIn. Thanks for joining, stay in touch, and don't forget to keep asking your engineering questions.